Hello everyone, welcome back to our channel Adi Vigyan Engineering. Today we will learn about multivariate calculus. So see, calculus is very important in science and technology. Functions of one variable we know, but functions of two or more variable is more important in science and technology. So there are many applications of calculus such as in the study of electricity, fluid dynamics requires multivariate function. So today we'll learn about functions of two or more variables. So let's start. See, let us say we have z equals to f of x, y. So this z is a function of x and y. If we talk about example, let us say z is x square plus xy. So it's a function of z is a function of x and y. Okay. So remember here x and y are two independent variables. Okay. So if we extend this knowledge for, let us say, for four variables, let us say we have z as x1 square plus 2x1 x3 plus x4 x2. Okay. So here we can see that z is a function of x1, x2, x3 and x4. So we can write f of x1, x2, x3 and x4. This is x1 square plus twice x1 x3 plus x4 x2. See, as function of single variables, the calculus can be developed for function of several variables also. That is the concept of limit, continuity, differentiability can also be applied for multivariate calculus. So let us first see what is the geometrical interpretation of a function of two variables. So geometrical interpretation of a function of two variables. So let us see. See, in case of function of a single variable, we had seen that usually a function represents a curve in two-dimensional plane. In case of function of two variables, let us say z equals to f of x comma y. This function represents a surface in three-dimensional space. So we can say this represents a curve in three-dimensional space. Okay. So this is the interpretation. Let us take one example. If we have a function z which is defined as 3x plus 2y, this function represents a plane. This represents a plane. And if we talk about z equals to square root of 2 minus x square minus y square, this represents the surface of a sphere in three-dimensional space. So this represents the surface of a sphere in three-dimensional space. Okay. Now let us see one diagram. Let us say we have this three-dimensional space. This is your x, y, and z. And in this three-dimensional space, let us say we have a surface. Let's say we have a surface, something look like this. This is the surface. Okay. And let us take one point in this three-dimensional space as x, y, z. So this is your x value. This is your y value. So this coordinate is x comma y, and this height is z. Okay, this height is z. So in this figure, we show a position of xy on XOY axis, XOY plane, and the corresponding value of z. Hence a point, let us say this is the P point, Pxyz lies on the surface given by z equals to f of xy. Okay. Now let us see our next topic. Now we want to find the limit and continuity of a function of two variables. Okay. And meaning of a variable point x comma y tending to a fixed point a comma b. So let us see another diagram. This is your x, this is y, this is z. This is your origin O. Let us say this is the surface. This point is x comma y, and this point is a comma b. So let x comma y be a variable point, and a comma b is a fixed point. on x over y plane. If x and y, this x and y vary in such a way that the variable point x comma y lies within any arbitrary region, whatever small may be. Let us say that region is R, surrounding the point a comma b. Then we say x comma y, this point, tends to a comma b. So we write x comma y tends to a comma b, or we can say x is tending to a and y is tending to b. Okay, so let us see limit or simultaneous limit of a function f of x comma y. So let z is a function of x comma y and is a function of two variables. Corresponding to each x comma y, we get a value z. So let x and y vary and x comma y tends to a comma b. Then z also varies, and if z tends to a number, let us say z is tending to a number l. Okay, so z tends to l. We say l is the limit of z. That is of f of x y as x comma y tends to a comma b. So we can write in limit form. So limit as x comma y tends to a comma b, f of x comma y, that is z, this will give the value l. Okay, this is the representation of limit in two variable. Now let us see continuity of a function f of x comma y. So a function z equals to f of x comma y defined on a region R is called continuous at a point a comma b if a comma b lies within the region R. And we say limit x comma y tends to a comma b f of x comma y gives f of a comma b. If f of x y is continuous at every point within the region, let us say within the region R, okay, within the region R, then we say f of x y is continuous in the region R. So let us see one question. So you will understand it more. Question is, find whether the limit x comma y tends to 0 comma 0, that is xy by x square plus y square exist. Hence find whether the function is continuous at 0 comma 0. So let us see. See here, let us say we have two functions, y as m1x and y as m2x. Remember, the slopes are not equal. So we can say that limit x tends to 0, m1x should be 0, and limit x tends to 0, m2x should also be 0. So let let us put this y value in this given limit. So we can say limit x tends to 0, x into m1x by x square plus m1 square x square. So this will be x square, and if you take x square common, it will cancel out. So it will be m1 by 1 plus m1 square, and limit x tends to 0. If we put this value, we can say this is x into m2x by x square plus m2 square x square. So it will be m2y 1 plus m2 square. Okay. So here we can see that limit x tends to 0, x into m1x by x square plus m1 square x square is not equals to, because this value is m1 by 1 plus m1 square, and this value is m2 by 1 plus m2 square. So this is not equals to limit x tends to 0, x into m2x by x square plus m2 square x square. So this means that limit x tends to 0 comma 0, which is xy by x square plus y square, does not exist. So the function is not continuous at 0 comma 0. So you can say the function is not continuous at 0 comma 0. Okay. Now let us talk about repeated limit. Repeated limit. Let f of xy be a function of two variables defined over a region R. A comma b be a fixed point, keeping y as constant. So Let me write it here. Keeping y constant, let x is tends to alpha, and consider the limit x tends to alpha f of x comma y if exist. Okay, and this is if exist. This will be function of y. Let us say, because here y is constant, so this will be function of y, say phi of y. Again we are considering that limit y tends to be phi of y uh, if exist, and suppose limit y tends to be phi of y is L. Okay, so thus we can say that limit y tends to b, limit x tends to a f of x comma y gives the value L. This limit is called repeated limit of the function f of xy as x tends to a. Let us say this is a. As x tends to a, and then as y tends to b, because whenever we put limit x tends to a f of xy, we got a function phi of y. Then we have put the limit y tends to b in the function phi of y, and we got a value L. So ultimately we can say that limit y tends to b, limit x tends to a f of x comma y gives the value L. So this is your repeated limit. Okay. Similarly, other repeated limit such as limit x tending to a, limit y tending to b, f of x comma y can also be constructed. And this is not ensured that the two repeated limits, that is this and this, will be always equal. There is no guarantee. Moreover, the simultaneous limit, this is your simultaneous limit, limit x tends to a, y tends to b, f of x comma y may not be equal to the repeated limit. Even it may happen that the two repeated limits exist and become equal, but the equal value is not the limit x tends to a, y tends to b, f of xy. So let us see one theorem regarding this. For a function f of x comma y, if limit x comma y tends to a comma b, f of x comma y exists and equals to L, and if both the two repeated limits, if both the two repeated limits, limit x tending to a, limit y tending to b, f of x comma y, and limit y tending to b, limit x tending to a, f of x comma y exist, then we can say limit x tending to a and limit y tending to b, f of x comma y is equal to limit y tending to b, limit x tending to a, f of x comma y is equals to L, right? So from this theorem we can say that if limit x tending to a, limit y tending to b, f of x comma y is not equals to limit y tending to b and limit x tending to a, f of x comma y. If this limit is not equals to this limit, then we can say limit x comma y tends to a comma b, f of x comma y does not exist. Okay, this should be equal. Otherwise, limit x comma y tends to a comma b, f of x y will not exist. So let us see one example so that this will be clear. Let us say we have the function of xy as x square y cube plus log of x log of y by y. Let us say we have this function. Okay, and let x tends to 2 and y is kept constant, because we have to vary one by one. So then we can say that limit x tends to 2 keeping y constant, f of x comma y would be limit x tends to 2, this function x square y cube plus log of x into this should be log of x into sine of y. Okay, so log of x into sine of y by y. So let us evaluate this limit. Here y is constant, so it will be 2 square y cube. We put the value x equals to 2 plus log of 2 into sine of y by y, because it is constant. So you can say that this is 4y cube plus log of 2 into sine of y by y. And in the next phase, let us consider y is tending to 0. So if now y is tending to 0, after calculation of x tends to 2, we can say limit y tending to 0, limit x tending to 2, f of x comma y would be limit y tending to 0, this function 4y cube plus log of 2 into sin y by y, and this 0 cube, 4 into 0 cube would be 0, and this is log 2 limit y tends to 0, sin of y by y is 1. So this will be log 2. Okay. Now let us calculate the opposite thing, that is limit x tends to 2, limit y tends to 0, f of x comma y. So that means in the first case we have to take x as constant for this limit, right? So let us evaluate limit x tends to 2, limit y tends to 0. This is x square y cube plus log of x into sin of y by y. So if you put 0 here, this will be limit y tends to 0, sin of y by y, this will be 1. This is log x is constant here, and if you put 0 here, you will get only log x. So limit x tends to 2, log of x. So if you put x tends to 2, you will get log of 2. So you can see that both the values are equal. So we can say that the two repeated limits are same. Okay. So that's how we represent this. Now let us see our next topic, which is partial derivative. Partial derivative. So let z is a function of x comma y. The derivative of f of xy with respect to x, keeping y constant, is called partial derivative of f of xy with respect to x, and it is denoted by delta f. This is not d, this is delta. Delta f by delta x, or we can represent this as f of x, x comma y. So that means this symbol represents that we are deriving the function with respect to x, keeping y constant. Okay. And we know the basic definition of derivative, that is delta f by delta x is limit h tends to 0, f of x plus h comma y minus f of x comma y by h. Okay. So this is when finally remember the notations, and this is the definition of partial derivative of f with respect to x. This is the partial derivative of x comma y. Okay. So whenever you are doing partial derivative of the function with respect to x, it will be x plus h, y is constant, so comma y minus f of x comma y by h. Similarly, if we derive the function with respect to y, keeping x constant, we can denote this as delta f by delta y or f y of x comma y. Okay. Now this again we can define that delta f upon delta y, this will be, let us say, limit k tending to 0 f of, now x is constant, so x comma y plus k minus f of x comma y by k is a partial derivative of x y, function of x and y. So remember these two things is very important. See, remembering this is very easy because whenever it is h tends to 0, h is here. Whenever it is k tends to 0, k is in the denominator. And minus f of xy is in both the differentiation. And whenever you are doing partial derivative of x, partial derivative of the function with respect to x, then you have to add h in x, keeping y constant. And whenever you are doing the partial derivative the function with respect to x, keeping x constant, so keep x constant and add k to y. That's how you have to remember. Now let us say we have a function z as x1, x2 in this manner. This is a function of n number of variables. So you can say that this delta z upon delta x2, let us say. So delta z upon delta x2 means delta del x2 of f. This z is the function f, right? So you can say that we are differentiating it with respect to x2. So here is the notation. See, here we are differentiating with respect to x, so fx. Here we are differentiating with respect to y, so it is fy. Here we are, let us say we are differentiating with respect to x2, so f of x2 of x1, x2, xn. And this, from the observation, we can say that you have to add h to x2, right? So this would be limit h tending to 0 f of x1 comma x2 plus h comma x3 up to xn. This will be same everywhere, f of x1, x2 up to xn by h. Okay. Now I think you have understood how to write this partial derivative. Okay. So unlike function of single variable, existence of partial derivatives does not ensure continuity of a function f of xy. Remember this. So let us say, let us see one question so that this topic will be more clear. Find, the question is, find from definition the partial derivative of the function f of xy is x to the power 3 by 2 into e to the power y with respect to x at the point 1 comma 2. So it is clear that we have to find f(x) 1 comma 2, right? We have to derive the function with respect to x. So it is f(x) 1 comma 2 at the point 1 comma 2. So we can write this as del f upon del x at 1 comma 2. So what is the definition? We know the definition. The definition is limit h tends to 0 f of we are deriving it with respect to x. So f of x plus h. What is x? That is 1. So 1 plus h comma y, that is 2, minus f of x comma y, that is 1 comma 2 upon h. Now our f of x comma y is this function x to the power 3 by 2 comma e to the power y. So in place of x we have to write 1 plus h, and in place of y we have to write 2. So let us write. So limit h tends to 0. This is in place of x we have to write 1 plus h. So this should be 1 plus h to the power 3 by 2. This is e square minus f of 1 comma 2. So in place of x you have to put 1, and in place of y you have to put 2. So 1 to the power 3 by 2 is 1 e to the power 2. It's minus e to the power 2 upon h. If we take common e to the power 2 outside the limit, so it will be e to the power 2 limit h tending to 0, 1 plus h to the power 3 by 2 minus 1 upon h. So let us put z equals to 1 plus h. So if h tends to 0, z will be tends to 1. Okay. So we can say that this limit is e to the power 2 limit z is tending to 1. This is z to the power 3 by 2, and we can write 1 as 1 to the power 3 by 2 upon this h is z minus 1. So this is our exponent formula. This is e square multiplied by, this should be our 3 by 2 into e to the power 3 by 2 into a to the power, that is 1 to the power n minus 1. It is 3 by 2 minus 1 n into a to the power, which is n minus 1. Okay. Now this is 1 to the power something is 1. So this is 3 by 2 into e square is the answer. Okay. So now let us move forward and see another question. Let's say we have this question. If theta is e to the power n e to the power minus r square by 4t, find what value of n will make 1 by r square del r of r square into del theta by del r is equals to del theta by del t. So let us see this question. So here theta is given as t to the power n e to the power minus r square by 4t. Now here we can see that we have the partial differentiation of theta with respect to r. So whenever we do the differentiation with respect to r, t will be constant. Okay. So let us first find out del theta upon del r because we need this. So t is constant. So t to the power n and e to the power x is e to the power x. Okay. And now for minus r square by 4t, minus 1 by 4t is constant. So keep it outside. And for r square, differentiation would be 2r. Okay. Now t to the power n, e to the power minus r square by 4t. This term is theta. So you can see that this is 2 and 4 will cancel out. So it will be minus r theta upon 2t. Now multiplying this with r square, you will get r cube minus r cube theta by 2t, and then you have to partial derivative with, then you have to again differentiate partially with delta r. So let us do it. Del r of r square del theta by del r would be del r, and r square multiplied by this, that means minus r cube theta by 2t. So minus 1 by 2t is constant, keep it outside. Now you have to apply u into v rule. So if you keep theta for r cube, it would be 3r square, and if you keep r cube for theta, it would be del theta upon del r. Okay. Now we know the value of del theta upon del r, which is minus r theta by 2t. So let us put the value minus 1 by 2t. This is 3r square theta plus r cube into minus r theta upon 2t. So this will be minus 1 by 2t, 3r square theta minus r to the power 4 theta by 2t. Then what we have to do? We have to multiply by 1 by r square. So 1 by r square del r of r square into del theta upon del r would be, here we can take common r square, and this r square and this r square will cancel out. It will be, and we can take theta common as well. So minus theta upon t, this is 3 by 2 minus r square by 40. Okay. We multiply by 2, these two, it will be 3 by 2. This r square and 1 by r square cancels out, and we have taken theta outside, so it will be minus 3 by 2 minus r square by 40. Now in the right hand side we can see that we have del theta upon del t. So let us derive the function with respect to t. So del theta upon del t would be taking much space now. Del theta upon del t would be del t of the given function, that is t to the power n, t to the power minus r square by 40, t to the power n, t to the power minus r square by 40. So now we are deriving it partially with respect to t, that means now r is constant. Okay, so in this case we have to apply u into v rule. So let us keep e to the power minus r square by 40 as it is. T to the power n differentiation is n into t to the power n minus 1. Now keeping t to the power n as it is, for e to the power x differentiation is e to the power x, so it will be e to the power minus r square by 40. Now minus 1 by 40 minus r square by 4 is constant now, so minus r square by 4 will come outside, and differentiation of 1 by t is minus 1 by t square, so it will be plus 1 by t square. Okay, now if we see that this t to the power n, here we can write this as t to the power n by t. Okay, t to the power n by t, so e to the power minus r square by 40 into t to the power n is your theta, so this would be theta into n by t, and here again t to the power n e to the power minus r square by 40 is theta, so it would be theta into r square by 4t square. So if we take theta by t common, it will be n plus r square by 4t. So from this, okay, now it is given that we have to find the value of n, so that means this thing is equals to this. So let's equalize. So minus theta by t 3 by 2 minus r square by 40, this is equal to theta by t into n plus r square by 40. This theta by t will cancel out. This will be minus 3 by 2 plus r square by 40. This will be n plus r square by 40. This will cancel out, and n is minus 3 by 2. So n is minus 3 by 2. So if n is minus 3 by 2, then this left hand side would be equals to right hand side. Okay. Now let us move forward, and now let us talk about higher order partial derivative. Higher order partial derivative. Let us talk about this. See, let us, for simplicity, we consider a function f of xy of two variables. Okay. Now, fx x comma y and fy x comma y are also function of x and y, because the values of partial derivatives may vary from point to point. The partial derivative of fx x comma y and fy x comma y are called second order partial derivative. So here we have four kinds of second order partial derivative of f of xy. The first one is, if you are deriving this derivative, because this is the partial derivative of the function f of xy with respect to x, keeping y constant. Again, you are differentiating with respect to x partially. So it will be del x of fx x comma y. We can write it as del x of delta f upon delta x. This is your delta f by delta x, and this should be del 2f by del x square, and we can write this as del 2f by del x square as f of x x. Now, second one is del y of f of y of x comma y. This should be del y of, this is your delta f by delta y, and this is del square f by del y square, and we can write this as f y y. Okay. Now, third one is del x of fy x comma y is del x. This is del x of f of y x comma y means delta f by delta y. So we can write this as del 2f upon delta x delta y, and this is f of x y. Okay. Now, del y of fx x comma y would be del y of this fx x comma y means del f by del x. Now, this is del 2f upon del y del x. So this is f of y x. These are the four derivatives you have to remember. Okay. And if we talk about the definition of second order partial derivative, so we can say that f of x x of a comma b is limit h tending to 0 if x a plus h comma b, because we are deriving x with respect to x, right, with respect to x, so we have to add h with a, minus fx a comma b upon h, and we can say if y of a comma b is limit k tending to 0, if y a comma b plus k, now here we are deriving with y, minus f of y a comma b upon k, and f of xy a comma b, this is limit h tending to 0, this is f xy. That means first we have found out with respect to y. So fy, and now we are finding out with respect to x. So fy a plus h comma b minus f of y a comma b upon h, and f of yx a comma b would be, don't confuse, this is not in multiplication, this is inside the function. So limit, let's say k tending to 0, now we have to add in y. If x function is x, because the first function is partial derivative of x, if x a comma b plus k minus fx a comma b upon k. So remember this whole thing because it is extremely important. Okay, this thing is extremely important. If any of the above limits, this limit does not exist, we say the corresponding partial derivative does not exist. So each of them should exist. Now remember that fxy ab may not be equals to fyx ab for every function f of xy. Okay. Now let us see one question to clearly understand this topic. So question is, given the function f of x comma y is xy x square minus y square upon x square plus y square, x comma y not equals to 0 comma 0, and it is 0 if x comma y is 0 comma 0. Find from definition if xy 0 comma 0 and if yx 0 comma 0, verify whether if x comma y 0 comma 0 is if yx 0 0. So let us see the solution. So according to the definition, we know that if x comma y, a comma b, that is here it is 0 comma 0. So here x is first and y, here y is first and x is second. So that means limit h tending to 0, y is first, that means f of y of, and x is second, that means you have to add h with x. So this should be a plus h, that means 0. A is 0, b is 0. So 0 plus h comma 0 minus fy 0 comma 0 upon h. So we can say that this is limit h tending to 0, f of y, this is h comma 0. So f of y h comma 0, this is minus f of y 0 comma 0, 0 comma 0 upon h. Okay. Now we have to calculate this value f of y h comma 0. So now f of y h comma 0, that is a is h, b is 0 now. So let us say this is limit k tending to 0, f of, we have to add k with, we have to add a, b with y. So this is f of h comma 0 plus k minus f of h comma 0, that is a comma b by k. So this should be limit k tending to 0, f of h comma k minus f of h comma 0 upon k. Now we know f of h comma k, this is this function when x and y is not 0. Okay. So let's see. It will be limit k tending to 0, h comma k. That means in place of x we have to write h, and in place of y we have to write k. So this should be hk, h square minus k square upon h square plus k square minus, now you have to put h in place of x and you have to put 0 in place of y. This is minus h into 0, that means whole term would be 0, but still we have to write h square minus 0 square upon h square plus 0 square by k. Now this term is 0, so you can say limit k tending to 0, h into this k and this k will cancel out, h into h square minus k square by h square plus k square. And if you put 0 in place of k, h square will cancel out, you will get only h, right? So we can say that f of y when 0 comma 0, that means in place of h if we put 0, then it should come 0 because here h is 0, right? So from this, let us say this is our equation 1. Now from this we have to put all the values. So we can say f of x comma y, f of x y 0 0, this should be limit h tending to 0, f of y h comma 0 is h, this is h, and f of y 0 comma 0 is 0, upon h. So h cancels out, it will be 1. Okay. Now let us find out the value of f of yx 0 comma 0. Now here x is first, y is second. So it will be limit k tends to 0 if x 0 comma 0 plus k upon minus fx 0 comma 0 upon k. Okay. Now this would be limit k tending to 0 f of x 0 comma k minus f of x 0 comma 0 by k. Now we need this value f of x 0 comma k. So let's find out f of x 0 comma k would be limit h tending to 0 f of 0 plus h comma k minus f of 0 comma k upon h. So this would be limit h tending to 0 f of h comma k minus f of 0 comma k upon h. I have to follow the same process. In this function we have to put the value. In place of x we have to put h, and in place of y we have to put k. So we will get limit h tending to 0 h into k h square minus k square upon h square plus k square minus 0 into k 0 square minus k square upon 0 square plus k square by h. So this term will be 0. So you'll get limit h tending to 0. This will be hk by h will cancel out. You will get k times h square minus k square by h square plus k square. If we put h change to 0, it will be minus k square by k square. Cancel out. Here you will get minus k. And if you put 0 in place of k, that means f of x 0 comma 0, this should be 0, right? K is also 0 here. So let us say this is our equation 2. So we have to put the values we get in this equation. So you can say f of yx 0 comma 0, this would be limit k tending to 0 minus k minus of minus 0 upon k. Okay, f of x 0 comma 0 is 0. Okay, we don't have to give minus 0, this is 0. So k and k will cancel out, it will give minus 1. So clearly we can see that f of xy 0 comma 0 is not equals to f of yx 0 comma 0. Okay, that is the thing we have to verify. Now see, from this question it is clear that f xy x comma y may not be equal to f yx x comma y for every function f of x comma y. Okay. Now there are some theorems which state the condition under which the above equality holds. Among those theorem, Schwarz theorem is considerable. Okay. Now we are not going into that thing. So moving forward to our next concept, which is functions of functions. That is, we have to apply chain rule. Functions of functions. Chain rule. So let us say we are finding out here the chain rule for function of two variables. So let f of u be a differentiable function of u, and u is a function of x. U is a function of x. So we can say that f is also a function of x. So the derivative delta f upon delta x, this we can write it as delta f upon delta u multiplied by delta u upon delta x, right? So this is the derivative. Now let us say f of u be a function of u, and u is a function of, here u is a function of x and y. So we can say that f is also a function of x and y. So there are two partial derivatives, right? Delta f upon delta x, which would be delta f upon delta u multiplied by delta u upon delta x. We can write this. Delta u cancels out, it will be delta f upon delta x. Now delta f upon delta y, we can write this as delta f upon delta u multiplied with delta u upon delta y. Now let us see another scenario. In this scenario, let f of u comma b be a function of u and b. Here u and b are function of x and y. So f becomes a function of x and y. Now we have to derive this with respect to x and y. So let us say delta f upon delta x. This we can write it as delta f upon delta u into delta u by delta x plus delta f upon delta v into delta v upon delta x. Okay, because f is a function of ub and ub is a function of x and y. So if we are deriving this f function with respect to x, then we need delta f by delta u into delta u by delta x plus delta f by delta v into delta v by delta x. And we can write delta f by delta y as delta f by delta u into delta u by delta y plus delta f by delta v into delta v by delta y. Okay. Now, if there is another scenario, let us say f of u comma v be a function of u and v, and here u and v are function of x only. So we can say that f is a function of x. So here we have to apply the ordinary derivative, not the partial derivative. So ordinary derivative is df by, because here the function is only x, depends on x only. So df by dx, this we can write it as delta f by delta u into du by dx and plus delta f upon delta v into dv by dx. So in this scenario, all the scenarios, we have assumed that all the derivatives actually exist, and these are known as chain rule. Okay. So let us apply the chain rule. Then you will see that this is not actually difficult. So let us see one question. Let us say we have this question: if y is log of u square plus 1 and u is sine of x, find dy by dx. So see here, y is a function of u and u is a function of x, and you have to differentiate y with respect to x. So in these scenarios, we apply the chain rule. See, we can write it dy by dx as dy, and it depends on u. So dy by du into du by dx. Right? It is as simple as that. Du cancel out, it will be dy by dx. So you can say du of log of u square plus 1, and this is ddx of sin x. So log x differentiation is 1 by x, and for u square it will be 2u. Differentiation of sin x is cos x. So u is sin x, so this is 2 sin x cos x, so we can say this is sin 2x upon 1 plus sin square of x. Okay, this is the answer we need. Okay, now let us see another question so that it will be more clear. If z is u square plus v cube, where u is sine of xy and v is y square, find del z by del x and del z by del y. See here, z is function of u and v, u is function of x and y. b is a function of y. So, and we have to find delta z upon delta x. So, we have to apply chain rule. Delta z upon delta x. So, we can write this as delta z is a function of u and b. So, let us write one by one. First, delta u into delta u by delta x, and second, it's a function of b also. So, this is delta z upon delta v into delta v upon delta x. Okay, now let us see. This is del u, z is u square plus v cube into del x of u, u is sine of xy, plus del v of z, z is u square plus v cube into del x of v cube. B is, sorry, del x of, this is v, v is y square. So let's see what it would be. Differentiation of u, partial derivative, here v is constant, so it's 2u and multiplied with partial derivative of sine of xy. So sine of xy differentiation is cos of xy, and here y is constant, so y will come outside, and for x it will be 1, plus here u will be constant, so it will be u square, sorry, u square is 0, sorry, this is 3v square, because u is constant, differentiation of constant is 0, multiplied with, here it is only y square, and we are differentiating with x, so it will be 0, so whole term is 0, so it is y into, this is 2y u cos of xy. Okay, so we can say this is 2y cos of y is, u is our sin x, so we can say 2y sin x, 2y sin x into, I think, let me check, sorry, u is sin xy and cos of xy, so 2 sin x cos x would be sin 2x, so it would be y sin 2xy. Now we need delta z upon delta y, so similarly we have to proceed. Delta z upon delta y would be delta z upon delta u into delta u upon delta y plus delta z upon delta v into delta v upon delta y. So if you differentiate, z is u square plus v cube with respect to u. So v cube is constant in first case. So after derivative, we will see it will be 2u into x cos of xy plus 3v square into 2y. So this will be 2x sine of xy, cos of xy, because u is sine of xy, plus 6y, and v square, v is y square, so it will be y to the power 4. So this is x into 2 sine theta cos theta sine 2 theta, so it will be sine 2 xy plus 6y to the power 5. Okay, now what if there are 3 or more variables? So how to apply chain rule for 3 or more variables? So let us see this part. Okay, let us see chain rule for functions of 3 or more variables. Okay, chain rule for functions of 3 or more variables. Let us see this. See, let us say we have function u as function of x1, x2 in this manner xn, where x1 is a function of r1, r2 in this manner rp. Let us say x2 is a function of r1, r2, rp, and in this manner xn is a function of f of n, r1, r2, rp. Then we can say that delta u upon delta rk would be delta u upon delta x1 multiplied by delta x1 upon delta rk plus delta u upon delta x2 into delta x2 upon delta rk. In this manner it will go delta u upon delta xn into delta xn upon delta rk. And if we say that if x1, x2, xn are functions of only one variable, functions of only one variable, let us say s, then we can say that du by ds would be delta u upon delta x1 into d of x1 by d of s plus delta u upon delta x2 into d of x2 upon d of s. In this manner it will go delta u upon delta xn into d of xn upon d of s. So let us see one question to clarify this thing. Okay, let us say we have a question which is if v is z sine of y by x, where x is 3r square plus 2s, y is 4r minus 2s cube, z is 2r square minus 3s square. Then find del v upon del r and del v upon del s. So by chain rule we can say that del v upon del r, we can write it as del v upon del x, because we have xyz, into del x by del r plus del v upon del y into del y upon del r plus del v upon del z into del z upon del r. So this will be del v upon del x. So if you derive partially with respect to x, z and y would be constant. So in that case, this z will be constant and sine of y by x would be cos of y by x, and y is constant here, so it will be outside. Okay, sine of y by x would be cos of y by x, and we are deriving it with respect to x, and y would be outside, and 1 by x differentiation is minus 1 by x square. Okay, and del x upon del r, that means this differentiation, s will be constant now, so it will be 6r, so into 6r. Similarly, we can find this as z into cos of y by x into 1 by x into 4. I think you got the point. Okay, how to find this sine of y by x into 4r. So this will be minus 6 r y z upon x square into cos of y by x plus 4z upon x cos of y by x plus 4r into sine of y by x. And next we need del v upon del s. So let's find out del v upon del s. So it will be del v upon del x into del x upon del s plus del v upon del y into del y upon del s plus del v upon del z into del z upon del s. So I think you know how to calculate this. I am writing it here. Kindly match on your own. This will be z cos of y by x into minus y by x square into 2 plus z cos of y by x into 1 by x to minus 6 s square plus sine of sine of y by x into minus 6s. Okay, and if we simplify, it will be minus 2iz upon x square cos of y by x minus 6s square z upon x cos of y by x minus 6s sine of y by x. Okay, that's how you have to calculate. Now let us see one question. Let us see another question. If phi of v square minus x square, v square minus y square, v square minus z square 0, where v is function of xyz, it's given. Show that 1 by x into del v by del x plus 1 by y del v by del y plus 1 by z del v by del z is 1 by v. We have to show this. So let's see the solution, how to solve. So let a is v square minus x square, b is v square minus y square, c is v square minus z square, be three functions of xyz and v. Okay, because a, b, c are function of x, y, z and v. So we can say that phi of a, b, c as given, phi of a, b, c is 0. Now if we differentiate both sides with respect to x, that means del phi by del x would be 0. So let's differentiate by chain rule, because here phi is a function of abc now, right, and abc are function of x, y, z and v. So let's calculate. We can say this is del phi upon del a into del a of del x plus del phi upon del b into del b upon del x plus del phi upon del c into del c upon del x. This should be 0. Now if you see the function a, b and c, first derive this function with respect to a. So let's keep as it is, because we don't know this del phi by del a, but del a by del x. So you have to derive this function partially with respect to x. That means in that case v is constant. So you will get, and it is given that v is a function of xyz. So you cannot take v as constant, because it is given that v is a function of xyz. So that means what we can do is v square differentiation is 2v, and for v it will be del v by del x. Okay, and for x square it is minus 2x plus del phi upon del b into, again what we have to do, we have to partial derivative the b with respect to x. So in this case y will be constant and v is a function of x, y, z. So it will be 2v into del v upon del x minus 0 plus del phi upon del c. It will be 2v del v upon del x minus 0, and that is 0. So if we calculate, it will be v times del phi upon del a into del v by del x minus x, because we are taking 2 common and equating to 0. 0 by 2 is 0. Minus x, this is minus x into del phi upon del a plus this is v into del v by del x into del phi by del b. So v into del phi by del b into del v by del x plus this is 0 into this 0, v into del phi upon del c into del v upon del x. This should be 0. So you can say that v into del v upon del x, if we take common, okay, so it will be, we have to take common from this term and this term. So it will be del phi upon del a plus del phi upon del b plus del phi upon del c. We have to take this term in the right hand side. This is x into del phi upon del a. Okay. Now v by x, del v upon del x, this is del phi upon del a plus del phi upon del b plus del phi upon del c. This is del phi upon del a. Now v by x into del v upon del x, this would be del phi upon del a by del phi upon del a plus del phi upon del b plus del phi upon del c. Okay. Now similarly we can show that this is b by x into del b by del x is this thing. Okay. Similarly we can show that b by y into del v upon del y would be del phi upon del a by del phi upon del a plus del phi upon del b plus del phi upon del c, and v by z into del b upon del z, this would be del phi upon, this is b by x, so this is b by y, this is b, and b by z, it would be del phi upon del c upon del phi by del a plus del phi by del b plus del phi by del c. And if you add these three terms, that is b by x into del b upon del x plus b by y into del b upon del y plus b by z into del b upon del z, this will give 1 because in the denominator we have the same terms, and in the numerator we will get del phi by del a plus del phi by del b, and del phi by del c, it will cancel out. So it will give 1. So if we take v common, we can say 1 by x into del phi by del x plus 1 by y into del phi by del y plus 1 by z into del phi by del z. Okay, this would be 1 by v. This is del v, not phi. Sorry, this is del v. These are v. This is the proof we have to show, right? So I think you got the point how to solve this type of questions. Now let us move forward and see differentiation of implicit function. Differentiation of implicit function. So what are implicit function? Let us say we have an equation f of xyz equals to 0, defines one variable, let us say z. In terms of function of other two variables, let us say x and y. In that case, z is called implicit function of x and y. Okay, so if we have z is a function of x and y, okay, so we can say that f of capital F of x, y, and z is a function of x and y. So f of x comma y is small f. This should be 0. So here z is called the implicit function of x and y. Okay. So let us see one example. It's not difficult. Let us say we have x square plus y cube minus p square, which is 0. It's an equation, right? And from this we can express p as x square plus y cube to the power half. So we can say that t is a implicit function of x and y. Okay. If we take another example, let us say x plus y square is 5. It's an equation. So from this, if we say that x is 5 minus y square, so in this we will say that x is a implicit function of y. Okay, that's how it goes. Now let us see theorem regarding implicit function. First theorem is for two variables, one equation. Okay, so let's see the theorem. If f of x comma y is 0, gives y as an implicit function of x in a region on xy plane, then dy by dx, it would be minus of del f by del x by del f by del y, provided del f by del y not equals to 0. Okay, now here is the thing you have to remember. If this function gives y as an implicit function of x, then you can write dy by dx as minus delta f by delta x by delta f by delta y. Let us see our second theorem, that is for three variables, one equation. Okay, this is for three variable, one equation. So let us say if f of xyz is 0, gives z as an implicit function of x and y in a region on xy plane, then number A, delta z upon delta x is minus fx by fz, and B, delta z upon delta y is minus f of y by f of z. And remember, here fz should not be 0. Okay, so this is the thing you have to remember, that if f of xyz is 0 and this gives z as an implicit function of x and y in the region xy plane, so we can say that delta z upon delta x, we can write it as minus f of x by f of z, and delta z upon delta y, we can write it as minus of f of y by f of z. Okay, so let's see one question so that this thing will be clear. Let us say find dy upon dx if cos of x to the power y is sin of y to the power x. Okay, so see, this is cos of x to the power y minus of sin of y to the power x should be 0. So we can say that f of, let f of x comma y is cos of x to the power y minus sin of y to the power x. Now what should be f of x? This f of x means partial derivative of this function with respect to x. So that means this should be y into cos of x to the power y minus 1, and differentiation of cos x is minus sin x, minus this is sin y to the power x into log of sin of y, because when you are differentiating this function with respect to x partially, then y would be constant. So this is a to the power x format, and differentiation of a to the power x is a to the power x log of a. Similarly, we can find out f of y, that means delta f by delta y, keeping x constant. So here it would be cos of x. Now cos of x will be a, right, a to the power y. So this is cos of x to the power y into log of cos of x minus this x into sin of y to the power x minus 1, and differentiation of sin y is cos of y. Now by theorem 1, we can say that dy by dx is minus delta f by delta x upon delta f by delta y, that is fx by fy, we can say. Okay, so from theorem 1 we can say dy by dx, because we have to find out dy by dx, question is find out dy by dx, so it would be minus delta f upon delta x by delta f upon delta y. So let's divide it. So it will be minus y into cos of x to the power y minus 1 into sin of x. This is minus, right? So this is minus sin of y to the power x into log of sin of y. And here we have, this is 1 minus should be outside. So this would be cos of x to the power y into log of cos of x minus x into sin of y to the power x minus 1 into cos of y. Okay, now from the given relation, this cos of x to the power y is sin of y to the power x. Okay, so we can substitute. So this would be y minus minus plus, and this minus into minus, this will be plus. So y into cos of x to the power y minus 1 into sin of x plus cos of x to the power y into log of sin of y by cos of x to the power y into log of cos x minus x into cos of x to the power y upon sin of y into cos of y. So if we simplify, it would be y tan of x plus log of sin of y upon, if we divide by cos to the power y, okay, cos x to the power y, this would be log of cos of x minus x cot of y. Okay, this is the answer. So that's how you have to use these theorems. Now let us see another question so that it will be clear. Next question is, if f of x y z 0, prove that delta x upon delta y of z into delta y upon delta z upon x into delta z upon delta x of y, this is minus 1. You have to prove this. Okay, now from theorem 2 we know that delta z upon delta x is minus fx by fz, and delta z by delta y is minus f of y by fz. So from theorem 2 we can say that delta x upon delta y is minus f of y by f of x. Here z is constant, when z is constant. Okay, so we can say delta x upon delta y when z is constant is minus f of y by f of x. Similarly, we can say that delta y upon delta z when x is constant, it should be minus of f of z by f of y, and delta z upon delta x when y is constant, it should be minus of f of x by f of z. So we can say delta x upon delta y of z into delta y upon delta z upon x into delta z upon delta x y. This should be minus f of y by f of x into minus f of z by f of y into minus f of x by f of z. So it will cancel out. Okay. So minus minus plus minus minus. So it will be minus 1. Now let's move forward and see what is total differentiation. Total differentiation. Okay. So let us say that let z is a function of x comma y. Okay, z is a function of x comma y. Of z is a function of two independent variables. You can say x and y. And let change in x is dx and change in y is dy. Be the increments given to the variables x and y. So we can say that delta z should be f of x plus delta x because it's the increment, and y plus delta y minus original function f of x comma y. So this should be the increment, and this should give delta of f. Okay, this delta of f is called increment of the function, z f of xy. Okay, now let's see how to define differentiability and total differential. So again, let z of z is function of x comma y be a function of two independent variables x and y. The function f of x comma y is said to be differentiable or total differentiable at x comma y if f of x and f of y exists at x comma y, and if its increment delta z, or we can say delta f, can be expressed as if we can express the increment delta z as delta f upon delta x into del x plus delta f upon delta y into del of y plus epsilon 1 del x plus epsilon 2 del y. Okay, now this in turn we can say del f or z, del z upon del x into dx plus del z upon del y into dy plus epsilon 1 dx plus epsilon 2 dy. Now here epsilon 1 and epsilon 2 are variable depending on delta x delta y. Okay, and epsilon 1 tends to 0, epsilon 2 tends to 0 as delta x and delta y tends to 0. Okay, so the expression d of z delta z upon delta x into dx plus del z upon delta y into d of y. Okay, this expression, or if you write d of f, it should be delta of f by delta of x dx plus delta of f by delta of y into d of y. This is called total differentiation. Okay, this is called total differential, or simply differential of z or f of xy. So remember this, it is extremely important. Okay, here z is a function of f of xy. So d of z, you can write it as del z del x into dx plus del z del y into d of y. Okay, remember this is extremely important. Now let us see one theorem regarding this total differential. So theorem 1. If z is a function of x1, x2 up to xn, then we can say that d of z can be written as delta z upon delta x1 into d of x1 plus delta z upon del x2 into d of x2. In this way, we can say this is del z upon del xn into d of xn. Okay, where the variables x1, x2, xn may not be independent, and dz is total differential of z. Now let us see theorem 2 regarding this. So our theorem 2 is, if f of x1, x2 up to xn is c, that is a constant. Okay, c is a constant, then remember d of f should be 0. Okay, see existence of partial derivatives fx xy, fy xy do not ensure the total differentiability of f of xy at x comma y. Remember this point, and let us see total differential for second order differential. So let us see second order differential. Okay, so let z is a function of xy be a function of two independent variables x and y. The second order differential of z f of xy is defined by d square z. Okay, where this d square z is actually d of dz. This is your second order differential. Now let us see theorem 3. So our theorem 3 is, if z is a function of xy, is assumed to have continuous second order derivative, then we can say that d square z is del square z upon del x square into dx whole square plus twice del 2 z upon del x del y into dx dy plus del 2 z upon del y square into dy square. And number 2, you have to remember that d square z is del x into dx plus del y into dy whole square z. Okay. Now this theorem can be generalized also. Okay. Now if we have, let us see the generalized form. If we have z as f of x1 x2 in this manner xn, then our d square z would be del x1 into dx1 plus del x2 plus del x2 into dx2. In this manner it will go del xn dxn square z. Okay. Now remember one thing, that if x is independent, then d square x is 0. Okay. Now let's see some question to understand this topic more clearly, and after that we will wrap up this lecture. So just say question is, if z is equals to f of x comma y, which is x square y minus 3y, determine d of z when x is 4, y is 3 and del of x is minus 0.01. Del of y is 0.02. Okay. So let's see the solution of this question. So first of all, we have to find this d of z. So let's find it out. So delta of z, we know this can be written as f of x plus delta x, y plus delta y minus f of xy. This is our basic definition, right? So this is f of x, this is y. So in place of x we have to write x plus delta x, and in place of y we have to write y plus delta y. So if we substitute, this would be x plus delta x square into y plus delta y minus 3 times y plus delta y minus f of xy is this x square y minus 3y. So let's evaluate. It is a plus b whole square, and then we have to multiply with this. So after calculation you will get twice xy delta x plus x square minus 3, taking delta y common, plus delta x square into y plus twice x delta y plus delta x square into delta y. Okay. So we can say that this is twice xy delta x plus x square minus 3 delta y plus this is delta x into y plus twice x into delta y. If we take delta x common from this, and delta x square into delta y. Now twice xy delta x plus x square minus 3 into delta y. We can say this is epsilon 1 into delta x plus epsilon 2 into delta y. So this is in the general form. So here we can say that epsilon 1 is delta x y plus twice x delta y. Okay. Now if now this thing epsilon 1 tends to 0 as delta x tends to 0 and delta y tends to 0. If you put delta x tends to 0 and delta y tends to 0, it will be tends to 0, right? And epsilon 2, which is delta x square, which will also tends to 0 as delta x tends to 0 and delta y tends to 0. So we can say that the function f of xy is differentiable. So total differential is total differential is, we know this is the object and this would be only this thing. So 2xy delta x plus x square minus 3 delta y. In place of delta x and delta y, we can write dx dy. So 2xy dx and x square minus 3 dy. Now we have to find out when x equals to 3, y equals to 3, delta x minus 0.01 and delta y minus 0.02, then find d of z. So let's find out. So our d of z would be, let's put all the values, that is 2 into 4 into 3 into minus 0.01 plus 4 square minus 3 into 0.02. If you calculate, it will be 0.02, which is the answer. Okay. Now let's see our next question, which is if z is x square y minus 3y, determine d square z, second order differential, right? So let's find out. We know that d square z is defined as del x dx plus del y dy square into z. Now if you break this in terms of a plus b whole square, so it will be del 2 z by del x square into dx whole square plus twice del 2 z upon del x del y into dx dy square plus 2ab plus b square. So del 2 z del y square into dy square. Okay. Now let us say this is, now let's calculate one by one. That is del 2 z upon del x square. So we can write it as del x upon del z by del x. So what would be del z by del x? If you differentiate this with respect to x partially, keeping y constant, right? So it would be 2xy. Then differentiate again with x, so it would be 2y. Now del 2z upon del y square would be del y of del z by del y. So del z by del y means x is constant, so it would be x square minus 3. So again x is constant, 3 is already constant, so it will be 0, right? So let's calculate this. Del square z upon del x del y, which is del x of del z del y, which is del z del y is x square minus 3. So this is del x of x square minus 3. So this will be 2x. So let's put the value. So d square z would be twice y dx square plus 4x dx dy plus 0 into dy square. So this would be 2y into dx square plus 4x into dx into dy. This is the answer. So I think you have come to know how to solve partial differentiation, total differential, limit, differentiability. Okay. So this chapter is the basis of your calculus in engineering mathematics. So be very careful, and it will be applicable in physics and engineering subjects. Okay. So I think that's all for today. If you liked it, please like, share, and subscribe, and comment in which chapter you need a video, because here we are giving the solution of 4 engineering subjects like network theory, signal system, digital signal processing, digital electronics. Okay. And in this channel we will mainly focus on gate related subjects, and still if you have any doubts in other subjects, you can comment down. I will definitely upload a video. Okay. So that's all for today. Thank you. Have a good day and take care of yourself.